Next up, we have Brent Miszalski talking about Data Central Data Aggregation Service. Brent, you're up.
Thanks for the opportunity to speak to you today about Data Central's data aggregation service. The project was motivated by discussions with my colleagues about the FRB candidate requirements. So data aggregation in astronomy involves finding all data that you have available online for a given sky position and radius, for example, images and catalogues. And the Crafts survey team are doing a survey for FRBs with the ASCAP array in Australia, and they have a large uncertainty in target position that they want to investigate. Is there a host galaxy there? Is there a redshift in the literature? So there are several mature and powerful data platforms available to look for information online, Vizier, CDS Portal, and various others. However, checking each platform can be quite time-consuming and error-prone, especially if you have a large target list. So to fill this gap, we've developed the Data Aggregation Service, which is a web application that simultaneously queries multiple online data services. Query results are displayed in the browser and may be exported to TopCat or Aladin via WebSAM, and you can download the catalogues in various formats too. We use Aladin Lite to provide interactive visualization of images and catalogues together. And we convert HIPS, fits to HIPS format on the fly for display in Aladin Lite. The application takes in RA-DEC, field of view, and an error radius, which represents the uncertainty. And then underneath the service queries a whole range of different services. We have a number of innovative features that we have developed since refactoring the application. We had an earlier version in May this year, but now we've designed it to be much faster using asynchronous technologies. Here's a view of the application itself. On the left, you see Aladin Lite, which can be made bigger and shows you the images and catalogues. The catalogues at the top are displayed in tabs, and you can toggle them on and off. You can, with your mouse over, identify where a given entry in a table is in the image, and you can also load Vizier tables on demand. There's a Simbat name resolver to go to new targets, and images are shown at the bottom, for example, from SIA services. And we currently have a beta version online. The structure of the application is an ASCII application consisting of, that is served up by Uvicorn, which is a fast ASCII server. And the application consists of two main components, a Python socket.io server that enables real-time bidirectional event-based communication between the Python backend and the web browser. And the Python backend is, we use Starlet, which is an ASCII web framework that has a range of features, Ginger 2 templates, WebSockets, asynchronous background tasks, and so on. We have several dependencies that go with the application. I've already spoken about some. We use a wide range of IVOA, DAO services, various API endpoints, Vizier, in particular the ASU interface, a whole bunch of asynchronous Python packages, and so on. So to do the simultaneous queries of multiple services, we have asynchronous functions launched as background tasks. And these tasks may in turn spawn other background tasks, downloading multiple images, for example, or launching more complex pipelines. Task results are sent to the browser via WebSocket messages. For example, when a download is done, a message will be sent. And that message will contain data that was retrieved from the service or an image location on disk. The browser is listening for the messages that are on a particular namespace, and the results are added to the page when they're received. VO table and ASCII results are cached using Redis and converted to Pandas data frames internally for filtering and so on. FITS files are converted to HIPS format using Aladin and are cached on disk with their location also cached. So I'll go through some of the highlighted features. This shows one of the FRBs from the ASCAP craft survey team. We have a custom Redshift aggregator that queries Visio for UCDs with source.redshift, and we provide a RADEC catalog with Redshift and the columns that were extracted for the Redshift from that catalog that we found. We have multi-wavelength HIPS overlays. At the moment, just a few radio surveys. So for example, this is from the ASCAP REX survey. And this is just, displaying on top of a Gemini mosaic that we produce. We check if targets have coverage in the survey of interest using MockPy. We have authenticated data access using Data Central's CAS server for authentication. Each user that is logged in may belong to a particular group, for example, a SkyMapper group, and that allows us to provide seamless data access control based on group membership. For example, and so what we do, for example, for SkyMapper is we select the individual TAP and SIA servers depending on that group membership. So if they're Australian and have access to SkyMapper DR3, we provide that, otherwise DR2. And there's a lot of possibilities here with the authentication. And here you can see a SkyMapper image and TAP catalog displayed together. We developed DAS also as a testbed for pipeline as a web service technology, which we have developed in terms of reducing AAT data with 2DF. We use Celery underneath to prepare and schedule complex workflows to produce image mosaics. And on the bottom right here, you can see one of the workflows that we have. We have an initialization stage, then we download several files at the same time, different images, and then combine those, project them separately, and then combine them. So we've been doing this for SkyMapper, Gemini, and VLT4s. But launching these workflows is not easy. Single service queries are very easy to do from asynchronous functions. It's just a retrieval of a VO table. But for the heavier PAWS jobs, it can be a bit difficult. And we need to schedule these asynchronously. So we have a case of async inception here, where we use Celery, which is an asynchronous task manager, from an asynchronous function. The problem is Celery is not async IO compatible, and you do not want to wait for Celery task results and process what the outcome of a task is from an asynchronous function, because it will block or hang your entire program. So the workaround we use is to launch Celery tasks from asynchronous functions using task.delay. And that runs off in the background. From the task, we can post to an endpoint that we've set up using WebSocket, and then use WebSocket messages to raise errors and notify on completion. This shows you some VLT4s 2 mosaics that we make on the fly for NGC 6302. And the gray bar here is just the result of the mouse cursor moving over the list, the table of images. And as you move your cursor over, they are updated in the Aladin Lite display, allowing for a very seamless user experience. For larger images, we can add buttons to trigger downloads manually and provide a progress bar. Some of the Hubble WIFPIC 3 images are very large, so they take a little bit of time. The architecture that we've developed for DAS is repurposed. It can be repurposed to develop more sophisticated applications. This one we have developed is a target visualization and classification application. And we can, in this application, we import CSV targets into a Mongo database, and we can classify those targets using keyboard shortcuts or radio buttons, and then export the results. We use Aladin Lite to display each target individually, and you can also add catalogues on top of that and instrument footprints. The catalogues can be loaded up asynchronously using the same technology from DAS, and you can filter catalogues internally with the Pandas data structures as well. I'll be talking more about this next week at the Interop. But for the meantime, Michelle's talk earlier this week on the machine learning applications is really exciting as a possible application for this application, where you take candidates of interest, refine their classifications using this application, and then send the results back to the machine learning model. So I hope I've shown you a glimpse of DAS. It's a powerful and extensible platform for data discovery and visualization, especially for archival data using our pipeline as a web service platform. We hope to expand this pipeline as web service to reduce other spectroscopic and imaging data from multiple observatories. And this will really open up a new era of visualization and downloading of reduced data products without having to touch raw data or install pipelines, which is really quite innovative, I believe. We plan to improve table handling. At the moment, we just have some HTML tables, but there are some JavaScript packages that we can use. And these will allow users to customize column order and load up tables quicker. We may experiment with cross-matching of tables. I already touched upon briefly the authentication that we provide. And this allows us to customize data sources depending on the user and their profile. For example, if they belong to a private survey team that has data available, we could make that available. We want to develop more themed profiles as well, radio data, time domain data, and incorporate other visualization packages such as a spectrum viewer that we have developed at Data Central, and perhaps even larger data formats. Yes, thanks, I'm done. Of course.
Thank you very much, Brent.